Welcome back to the channel. In this lecture, we will introduce the concept of integrated sensing and communications, which is very beneficial for 6G systems. So, for high data rate and low latency systems, the basic problem that we are facing right now in wireless communication sector is that there are less frequency spectrums that are available. In order to compensate for that, we intend to unify the sensing and communication parts in one radio frequency or in one signal transmission, which means to say that the same radio signal can be used for simultaneously transmitting the data and sensing the environment. So, two purposes are obviously the signal is being sent for communication purpose, but it can also be used for radar detection purposes. And if these two simultaneously takes place, then these systems are called integrated sensing and communication systems, ISAC systems. It means that the spectrum hardware and power resources are efficiently being used. This means that a spectrum is going to be used for communication purpose, hardware is going to be used for communication purpose, power needs to be transmitted for communication purpose. The same entities can be now used for sensing purposes as well. So communicating the information means we are talking about data symbols, the bandwidth, everything like that. And in case of sensing, it means that we now need the location, so to say, of the device or person, or we can also track the angle, the velocity of moving objects in the surroundings using the wireless signal that is being used for communication. And therefore, we can integrate the two systems, and therefore these systems are said to be integrated sensing and communication systems, right here. So it's the same communication systems, but it's not only being used for, I'm using C for communication, but rather it is also being used for sensing purposes, right? So the moving vehicles, you can track the moving vehicles in the same system. The signals are obviously being transmitted always being transmitted by the base station. So that signal can be received, and not only the communication part can be done, but sensing of the surroundings, like what are the stationary objects, what are the moving objects in the surroundings, all that can be done using the same communication signal. And such systems are said to be what are called integrated sensing and communication systems. What is the basic architecture? We unify the system where the same hardware, it is very important, the same hardware and frequency spectrum is being used, or the signal waveform, all these are being transmitted once only. The same thing can be used for communication and can also be used for sensing purposes. So when we talk about the communication part, it basically means transmitting the data between users or devices. But when we talk about sensing part, then in that case we detect and estimate the parameters of surrounding objects, such as range, what is the location of the vehicle right now, what is the velocity with which it is moving, what is the angle at which the signal is coming, what are the environmental features of a given urban area. So you can understand it's very important, and it's very application based, that the same spectrum, hardware and waveform can be used for two purposes, communication and sensing. Simple block diagram can be like, if you have an ISAC transmitter, then it sends a communication signal over the link to the user, you, and at the same time it sends a signal uh, which is coming from echoes. So how the radar senses the objects, it sends a signal and receives an echo. So that echo signal, which is reflected from targets, are also being sent to the eject receiver for the sensing purposes. So simultaneously both communication and sensing can be done. I've also made another block diagram to represent the same. In this case, there is a radio tower that needs to communicate to a mobile device, but at the same time, it is also fetching the information of a target, a moving target, so to say. So my communication device is this, so communication is this over communication link, and you can see that the target, which is here, is used for sensing link. So what happens, in first duration we send a signal to it, and then the target reflects the same signal and you receive the same signal back. In that way you have a round trip delay of tau I, and we estimate based on what is the round trip delay and the angle at which the EM wave is coming back from the target, to sense the object that is there in the vicinity of the mobile station. So the same tower over the same bandwidth is performing two actions which are different: communication and sensing. That's the basic concept, and this is called round trip delay. In which phases it can work, so I can divide it into three phases. First of all, is the transmitter phase. In the transmitter phase, the first operation is to send the waveform towards both the things. But you can understand that in communication, when we are sending, we need to perform the actions of encoding, modulation. All those operations are done, and a modulation and encoding can be done for communication purposes. And similarly, the same waveform, this is very important, the same waveform is being sent for as a probing signal. Why probing? Because it is going to sense the target, and this is for sensing purpose. So this is my first phase, which is called transmission phase. The second phase is reflection and reception. When we talk about reflection, it's about sensing. When we say reception, it's about the receiver. So the transmitted signal is directly attended by the receiver, and the data decoding is done, demodulation and is done, and the information is conveyed to the mobile receiver. So this is the communication part of it. But at the same time, the signal also gets reflected off by nearby objects like vehicles, buildings, and pedestrians who are moving there, and that returns an echo to the transmitter, and this performs the sensing part of it. And the final phase, the third phase, is that the signal processing phase. This is important. So signal processing is also done at two levels. The first level is communication phase. In communication, the extraction of information symbols from the received signal, that means demodulation, channel estimation, whatever is done, is the signal processing for the communication phase. And signal processing for the radar phase. So for the radar phase, that is for sensing phase, you sense the echo signal, you see what is the range, at what velocity the object is moving, and at what angle the EM wave is coming back. So these are my sensing phases. So this is communication and this is sensing. Again, the three phases. How can we do that in terms of mathematical modeling? So mathematical modeling can also be done for two phases, like for two separate applications. The first application is, say, communication. So when we talk about communication, or let us firstly define what is sensing. So for sensing, suppose the received signal is given by RT. So there will be n targets. There will be n targets which are available in any vicinity. So it will receive a summation of n copies here. The channel gains will be given by alpha I. If xt was my original signal, then the signals are all coming back after certain delays, and that is given by the round trip delays tau I. So ith component suffers a delay of tau I. And obviously, if the target is moving, there will also be what is known as Doppler shift. You can see that in my previous lectures, lecture number 2, that if there is a movement of radio receivers, then they change the carrier frequency at which the signals are coming by a certain bit, which depends on obviously the velocity of movement, the frequency of operation, and the angle at which the movement is going to take place. That frequency is called a Doppler frequency. So in sensing phase, the received signal will depend on round trip delay, the n number of copies that are being generated by n number of targets that are available in the vicinity, and the Doppler frequency. Of course, there will be a AWGN factor. So I have also defined it here. So alpha is my sensing channel gain. This is basically small scale fading, alpha I, that can be modeled using Rayleigh, Nakagami, and any residue distribution. Tau I is my time delay or range estimation, or you can say round trip delay. And FDI is the ith component's Doppler frequency shift due to the movement of the various objects in the vicinity of the receiver. So these are my entities. Apart from that, there is additive white Gaussian noise also in the modeling. So this is my sensing phase. This all is for sensing phase. What happens in the communication phase? In communication phase, we have done it many times in my channel. We receive the YT, which suffers a fading of H suffix C. The signal that was transmitted is XT. Remember, this XT and this XT were same. These are the same XTs. It's just that one is going to be used for sensing purposes, and now it's going to sending XT to the receiver, and we will have a communication channel noise, which is NCT. So basically here HC is the communication channel gain, small scale fading, again model using Rayleigh Nakagami any fading channel. NCT is the communication channel noise, and XT is obviously the information signal that was originally sent in this for the sensing phase also and for the communication phase also. Now, how do you build that in time? So, what are the timing structures which are used? One layman way of doing that is that we used one time for communication, another for sensing, again for communication, again for sensing. And this scheme is called time division ISAC systems. And you can completely understand that in this case, we are actually violating our own thing. We wanted to unify both sensing and communication, but in this case, we are doing one by one. Therefore, at one time, only one can be done. So, what is the major disadvantage? The major limitation, it is easy, of course. The advantage is here. It is easy. It is easy. But what is the main limitation? That it is inefficient use of time, because it cannot perform both the purposes at one time. So we can do what is known as frequency division, ISAC, FD ISAC. In FD ISAC, we can use one fixed frequency band, suppose F1 minus F2 for communication, and another F2 minus F3, suppose for sensing. So at the same time, we can see on this axis, at the same time, both communication and sensing can be done based on various frequency levels. So suppose communication is from F1 minus F2, this is from F2 minus F3. So both can be done simultaneously. And this is a bit better. It enables us to perform both the actions better, but uh, it requires more spectrum, because what you are doing, you are actually making frequency division. So one frequency is going to be used for communication, other for sensing, and that hampers the system. So what is an actual ISAC system? An actual ISAC system, the joint simultaneous ISAC, is about waveform level integration. So in waveform level integration, and that is what where we introduce the ISAC system, actually unifies it completely. What happens in this case, that there is only one signal. That signal is basically dually used. It is dually used. It is used for communication and sensing at the same time, like 5G OFDM waveform can be used. So there is a frame duration. We cannot go in detail in this lecture, but just a slide of it. The frame duration will have some preamble to say that the frame has started. In every frame, there are some preamble bits to suggest that at this moment the frame is getting started. Then there are data signals similar which are being sent. Then there are some pilot symbols which are there to firstly to check how the channel is behaving, and to differentiate it from the next frame, we use some guard band. So in this part, this is used for radar and communication, and this is used for communication and sensing. So, and this is used for the guard band is used for synchronization. So you can understand that the same waveform can be used for both the purposes. It is fully integrated. No time division or frequency division separation is required. But yes, of course, there is going to be a complex signal processing that is used in this mode. Only the research is taking place. What are the major advantages and takeaway of the ISAC systems? They are efficient use of spectrum. If we can use the third stage, third division multiplexing, in which we use waveform coding, then you can understand that we can use the same spectrum for both communication and sensing purposes. We can use hardware sharing. The same hardware can be used for communication and sensing at the same time. You can improve the sensing awareness, because you are going to send the signals for communication purpose in any way from the BTS. So if you can sense the near about uh, structure or multipath fading environment of the communication channel, then you might also will be aware of how dynamically the channel is actually changing because of movement of users, because of movement of vehicles, because of large buildings. You might also get an awareness about that. And low latency and high reliability, you can perform it, because once you sense the environment at the same time while you are communicating, you will know about your environment, the surrounding in which the signal is being transmitted. So the 6G communication and 5G communications, which say that the latency should be very small, of the order of microseconds, and reliability should be high. This needs that you are aware of the wireless communications devices. The base stations are aware of the various surrounding features in the near vicinity. What are the problems that are there? The problem is one about the mutual interference. So if you are using the same channel for communication and sensing needs a signal to come back at a tau I also. So which means that there is going to be mutual interference in the same hardware. There both the signals are being used for communication and sensing. So there is going to be mutual interference. This interference management between sensing and communication is of utmost importance. Schemes like rate splitting multiple ISs, and I'm going to make a separate video on this, are being implemented. Uh, which are going to be opted for interference cancellation schemes. Complex balancing of resource allocation is required because you are using two modes of communication, one for communication and one for sensing, and therefore you need to balance the allocation of resources also. So dynamic resource allocation, deep learning based resource allocation is what is going to be used. Beam forming strategies, this is very important, and there are multiple papers that are being done on this. So in beam forming, what happens is that multiple input, multiple output systems are being used so that they can steer the beams towards communication and towards sensing purposes. And frame duration based on functionality is also stringent. What are the research problems? Waveform, shape, and signal designs, beamforming and MIMO techniques, signal processing and estimation, machine learning and AI-based design, system level and network level research, hardware and prototyping. So these are basically security and privacy aspects. These are basically the research problems that are open in integrated sensing and communication systems. So this is all about integrated sensing and communication systems, ISAC systems, and we can subsequently develop how to solve these problems using mathematical analysis in subsequent lectures. Thank you.